John Dalton found that in a mixture of unreactive gases, each gas acts as if it were the only gas in that mixture. And this idea is going to help us understand pressure of different gases in the same container. So we like to say gases act independently of each other, no matter if they are the only one in the space or they're one of 100. So partial pressure. Partial pressure is the pressure exerted by that specific gas in the mixture. Again, it doesn't matter if it's the only gas or if it's one of 10. It is the pressure of just one gas that you are talking about. Now, this idea came from, again, what we just discussed, and John Dalton named it Dalton's law of partial pressure. And so what we can see here is we have three different gases, gas A, gas B, and gas C, and they are put together in one box. And so the pressure, the partial pressure of A, plus the partial pressure or the pressure just of gas B and the pressure of gas C, if you add all those pressures up and they're in the same unit, that gets you total pressure. So again, you can find the total pressure of an enclosed space of gases by just adding up the individual pressures of all that are in there. All right, and we're going to go ahead and utilize this idea to do some calculations. So we have a 100 ml sample. Immediately when I see that I have a sample and it's giving me a volume, I'm going to go ahead and put a V so I can see if I need to use an equation that I'm already aware of. A 100 ml sample of air exhaled from the lungs is analyzed and found to contain all these amounts. So we have nitrogen, oxygen, carbon dioxide at a certain temperature in Celsius. I know if I am in Celsius, I should be converting to grams, converting to Kelvin. And if I have grams, I need to be converting to moles anytime you're working with gases. But let's see what else we have to figure out here before we do that. What is the partial pressure of each component and what is the total pressure? So what we need to do is we need to solve for the pressure of each one of these, and then we're going to go ahead and solve for total pressure by adding the three up. So I'm just going to go ahead and show you a sample example of one of these. So immediately when I see what pieces of data I have, I know that I'm going to go ahead and use PV equals nRT. We call that the ideal gas law. And I'm looking for pressure. Now I'm going to go ahead and work on the pressure of just the first one. So I'm going to say the pressure of N2. And we like to put something below if it is referring to the item we're looking for. So we're trying to find the pressure of the N2. Now my volume, remember volume for PV equals nRT has to be in liters. So I'm going to go ahead and make this 0.100 liters. I just quickly converted that. And then I'm going to go ahead and I cannot put grams into a PV equals nRT equation, so I'm going to convert. Now you can convert before or you can convert inside. Just to save some time, I'm going to go ahead and do the math equation in the overall equation. So grams to moles of N2, and so 28.02. All right, so whatever that answer will be multiplied then by my R value, which because I want my pressures to be in ATM, I'm going to use the 0.08206. Now remember, it doesn't tell you what your pressure needs to be. So if you want to use the other R constant and then get your pressure in torr, that's also perfectly fine. As long as it doesn't tell you a specific unit, you can do with whatever works for you. So then I'm going to go ahead and take 35 plus 273 and get 308 Kelvin. Okay, so that's Kelvin. All right, now let's go ahead and set this up. And again, the whole goal here is to solve for my pressure of the first one, which is the N2. So I'm going to go ahead and do 0.0830 divided by 28.02. Multiply that by the gas constant, 0.08, multiply it by my temperature, divide by my volume, and my pressure of my N2 ends up being, I'm going to keep, how many sig figs? I'm going to keep 3 sig figs here, 0.749 ATM. So that is my pressure of my partial pressure, or just pressure of my N2. Now you're going to want to go ahead and do this 2 more times for the O2 and do the same thing for the CO2. The only thing you need to replace is the mole value here. Okay, so you can go ahead and use the molar mass of those and the grams provided. So let's go ahead, and I actually have the work on the next slide here. So I did this 3 times, the pressure of the N2, which you see we got the unit in ATM. We went ahead and did pressure of oxygen and pressure of CO2. Okay, and again, you can see here, I also showed the conversion of milliliters to liters. So just so you're not worried where that's coming from. All right, so now I have the partial pressure of 3 of the gases, all the gases in the container. So I have N2, O2, and CO2. Now the question also asked then to find the total pressure. So to find the total pressure, all I have to do is add all 3 of these up, and that will get me my total pressure of the system. And so therefore, my P total is 0.9388 ATM. Okay? Now, what if we're not given as much information as we were in that previous problem? Could we still solve for total or partial pressure? Yes. Now, another part of Dalton's law of partial pressure, other than the equation we were just using, which is, the total pressure is made up of how many gases there are in the container. It could be 1, it could be 100, right? It just depends on what you're looking at. There is another unit or variable we're going to be looking at here, and it is a capital X, and it is mole fraction. Now, mole fraction, there is 2 equations you can use for mole fraction. So to find the mole fraction of gas A, we're just saying gas A as an arbitrary gas, you can take the pressure of A, or the partial pressure of A, and divide it by the total pressure of A. Or you could to find the mole fraction, or the portion of the mole fraction is like the amount in moles that the gas is in the total container. You can actually do moles of A over the total moles, because sometimes you're given moles instead of pressures. And so both of these equations will be provided for you on an exam, and so will this Dalton's law of partial pressure. So I want to go ahead and show you how to use the mole fraction equations. So we have air in the air sacs in the lungs is as follows. They give you 3 pressures. We have nitrogens, we have oxygens, we have carbon dioxide, and we also have water vapor. And what is the mole fraction of oxygen? So if we wanted to, and it's nice to always write out what we have, because it kind of helps you just visualize what's going on. So we have 4 partial pressures, and so if we added those up, we could easily get total pressure, right? If we added those up, that could get us total pressure. Our whole goal here is to find the mole fraction, or the X value, for the O2. So we have 2 equations here. We have pressure of A over the total pressure, or we have the moles of that over the total moles. Well, we don't have moles, so we're going to go ahead and utilize this first equation. So I'm going to go ahead and write that. So we're going to do the mole fraction of the O2 is equal to the partial pressure of the O2 over the partial pressure of the total amount. So let's go ahead and solve for our total. Let's just go ahead and add up all of our amounts. So 570 plus 103 plus 40 plus 47. That gets me a P total. Shouldn't have to write that whole word out, but that's okay. 760 millimeters of mercury, which is actually 1 ATM. And so I can go ahead and place my partial pressure of my O2 and my total pressure and solve for my mole fraction. So my mole fraction of the O2 is equal to 103 millimeters of mercury over 760 millimeters of mercury. Now, units for a mole fraction. Let's think about this. If I have a millimeters of mercury divided by a millimeters of mercury, they are going to cancel each other out. So mole fractions actually have no unit. Okay, no unit, but we're going to keep around the same number of sig figs. So I'm going to go ahead and make this 0.136. No units for mole fraction. No units for mole fraction. Okay? All right, now, kinetic molecular theory. The kinetic molecular theory is basically rules that we understand about gases and how they react. Now, the issue is when we are talking about gas molecules, we're talking about them in very normal situations that we exist in. So kind of like low temperature and like low pressure as well. So there is a lot of calculations, all those laws, Boyle's, Charles Gay-Lussac's ideal gas law, that we are able to utilize because of this kinetic molecular theory. Now, this is an equation we have previously used before. The kinetic energy is equal to 1/2 m being mass, v being velocity in this case. Just a reminder, your mass, if you do have to use this equation, which I would provide for you if you needed it to, it needs to be in kilograms. And the reason why is because the kilograms and then velocity is usually meters per second, which would then be squared. Then this unit would end up being joules. So we have talked about that in the past. Just a quick reminder, kilograms is your mass unit for that. All right, let's go ahead and just briefly go through the postulates or the components of the kinetic molecular theory. Gases are composed of molecules whose size are negligible, meaning gas molecules are so small that we don't even consider them taking up actual space. They are there, but they don't have enough, they don't add together to create any sort of space that is measurable. Now, molecules move randomly in straight lines in all directions and at various speeds. So we're going to go ahead and imagine a closed box container here, and we have to imagine the way we draw gas molecules is we go ahead and draw straight lines. So they go straight and then they hit, and then what we call is they cause a collision on the side. So they collide with each other and the sides of the box, and then they continue on in another straight line path. Okay, and they go all different speeds. Now, the forces of attraction or repulsion between the two molecules, we call these intermolecular forces, are very weak or negligible. So I know we have not discussed intermolecular forces. Intermolecular forces are things that hold molecules together. For example, a glass of water, the water molecules are held together by something called hydrogen bonding. We have not learned that. If you take Gen Chem 2, that is one of the beginning chapters you're going to discuss. But gas molecules, what we want to know about them mostly right now is that they have no connecting forces. Okay, they are not attracted, nor are they repelled by each other. When molecules collide with each other, the collisions are elastic, meaning the energy is conserved. So when it hits, it doesn't just stop, it then continues on. For example, if you're playing pool with, a stick and a ball, you hit a ball and then that ball hits another one, hopefully, and then it moves forward. So that is considered elastic. And then the average kinetic energy of a molecule is proportional to temperature. This one is a really big, important concept here. And again, remember, you're never going to have to read these or write them verbatim. It's more like if you had a question, does this apply to the kinetic molecular theory? But as you increase the temperature, go ahead and write this. As temperature increases, your kinetic energy increases. So your gases are going to move faster at higher temperatures, okay, and slower at lower temperatures. Here's another example of that term, elastic collision. An elastic collision is one where there is no kinetic energy lost. So an example of that would be this setup here. You've probably seen the pendulum of the ball swinging. Now, when you hit, if you've never seen it, when the ball comes down, all the energy is transferred and then this last ball pops back up. Now, in a perfect world where no energy was lost to the surroundings, they would continue to go back and forth all day, every day until a force stopped it. But that doesn't happen. We know that each time it goes up a little less. Okay, until eventually the energy is lost and they are all sitting in a row here. But theoretically, in a perfect world, gases would lose no energy and they would continue to just go on and on and on. Okay, especially if this was a closed container and no energy was lost. Now, let's talk about the speed that gases move. So according to the kinetic molecular theory, or the kinetic theory, sometimes they call it that, molecular speeds vary over a wide range. So the distribution of these different speeds all depends on temperature. And as I said before, the speed of molecules increases as temperature increases. Okay, molecules have more kinetic energy. They have more movement. They collide more. Now, when they are moving, okay, there's two different terms we use for their movement through an area. So we have the term diffusion and we have effusion. Okay, diffusion and effusion. So diffusion is when a gas is in a new container, it is going to spread out as uniformly as possible. So in a container, you're going to see here on the right side that these purple and blue molecules spread themselves out so that they're, pretty equal throughout. They are not going to just be in one area of the container. Okay. Now, effusion here, I'm trying to say that so you can hear the difference. Effusion is if there's a little leak in something, like for example, a balloon, it's basically how fast the gas molecules would escape that little hole. Okay. So if you've ever had a diffuser at your house, Glade plug-in or something like that, the gas comes out of the Glade plug-in by effusion, and then as it goes through and kind of circulates through your room, that is called diffusion. So an example that you are seeing all the time, or any sort of, plug-in that allows that scent to be released. Now, how can we put an actual number to how fast or how slow molecules move against each other? The answer is yes. So it is called Graham's law. And Graham's law of effusion means that constant temperature and pressure, so we're not changing either of these, the rate of effusion, meaning a gas releasing itself through a hole, is inversely proportional to the square root. Okay? Now, I am going to give you this equation here on any exam, but the rate of the higher or the lighter gas over the rate of the heavier gas, and then the square root. So let's go ahead and do an example, and then we'll try one on our own. So again, the whole concept here is lighter gases in terms of mass move faster. Heavier gases move slower. Now, we want to say, can we figure out a way to figure out exactly what their relationship would be? And the answer is this, using Graham's law. So we have hydrogen and we have helium, and they are being used in blimps. If a small leak were to occur, which gas would effuse more rapidly and by what factor? So which one would come out faster? So what you're going to do is you're going to go ahead and create just a relationship. So the top here is just the rate of the H2 and the bottom is the rate of the helium. There's no numbers going on that left side right now. And to do this, the lighter gas, the molar mass goes on the bottom. Okay, so that is the biggest thing is you're going to have to notice. The lighter gas, when you add it up, the molar mass goes on the bottom. And the heavier gas, which we usually like to put on the bottom of the left side of the equation, the molar mass is on the top. So they switch places when you're solving for them. So H is H2, so there's two of them. So I put that on the bottom. I went ahead and did the mass of helium. So I'm going to go ahead and do 4 divided by 2. Then I'm going to take the square root of 2. Okay, and we are going to see that hydrogen will diffuse by a factor of about 1.41 times. So hydrogen will diffuse 1.41 times faster than helium if there were a small leak to occur in the blimp. All right, so let's try another example here. And I went ahead and calculated our molar masses just to save us some time. So calculate the ratio of diffusion rates of ammonia gas to hydrogen chloride, or HCl. Same temperature, same pressure. Now, to set this up, we want to go ahead and I always put, so I solve for the molar masses first, and then the left side, I go ahead and put NH3, or the lighter gas I like to put on the top. I said 3, I wrote 4. All right, NH3 gas on the top, and then I'm going to go ahead and just identify HCl on the bottom. And the reason why you have to identify that is so that you know where your values go. So the molar mass for NH3, the top one goes on the bottom, this goes on the top. You don't have to draw these lines, I'm just doing it to show you. So NH3 I solved there up above for us is 17.04. And HCl is 36.46. Now, the reason why, if you write it with the lighter gas on the top and the heavier massed gas on the bottom, that way when you're writing your relationship at the end, you can say, well, I'll show you actually here after I do it. So 36.46 divided by 17.04. Okay, then I'm going to go ahead and take a square root of that. Remember, you can always raise something to the half power if you're having trouble with any sort of square, how to square something, or you're welcome to ask me. So the relationship then is NH3 effuses 1.46 times faster than HCl. Okay, so if the number's above a 1, okay, then that means it's traveling faster, of course. So this is traveling about 1.5 times faster than the HCl. Now, let's say you had the HCl on the top and the NH3 on the bottom, and then you went ahead and flipped these. Then the way you write it would be different. You'd have to talk about your relationship in terms of HCl to the NH3. So again, the reason why I wouldn't even put too much thought into that, I would just kind of remind myself if I were doing this to put the lighter gas mass on the top of the left side to find the rate, and the bottom, the heavier one on the bottom.